Hey there, welcome back to Farmcraft. I'm John. We're working on my hydroelectric system, and in this video we're going to be working on the draft tube. There's the pipe for the system. The generator is going to be right there at that Y, and then the draft tube is going to come down and it's going to discharge underwater right here. There's been a lot of questions about the draft tube, and it's something that I've had to study on and learn a lot about. In this video we are going to build a draft tube, but first I want to go through what the draft tube is actually doing and why it is okay to have the generator up there and the draft tube down here. I'm not losing any efficiency in building it this way. In fact, I'm gaining. So we need to look at the draft tube and understand how it works, and then we're going to build one and install it. And I should mention, making a draft tube is not an easy thing, at least a properly designed one, because you have to go from your 6-inch pipe, which is what I'm using, but you'd go from whatever pipe size you're using and flare it out in all directions, making a cone-shaped pipe that flares, up to, like, in my case, I'm going to do 12 inches. But it's got to be a smooth, even flare. Nobody sells anything like that. You'd have to have it custom made. It would be extremely expensive. And I've thought a lot about how I wanted to build it, but we'll get to that a little later in the video. Okay, so this is how my system is set up. Here's the pond. There's the intake. It's submerged a few feet below the water. There's a turbine in there, and that's the generator. The Y is necessary because that's what allows you to get the shaft into the flow of the water, but then also be dry where the generator is. It then turns 45 degrees downward and discharges into the tailwater. Now on my system, this distance here, the total head is about 21 feet, which that equates to about 9 psi in water pressure. Which, by the way, is why you can't use a Pelton wheel on something like this. This is a low head system. Pelton wheels work with high head systems. If I only have 9 psi of pressure to work with, it's just not going to produce a powerful stream to hit the spoons and spin the turbine on a Pelton wheel. So that's why we're using an axial flow turbine. We've got lots of water flow. We can hit a propeller inside the shaft with a large mass of water, even though it's not under tremendous pressure. And in my setup, this is about 6 feet under the water, partially because the intake is several feet below the water, and then the rest of the drop is after. This is called the draft tube. So, very common question that I've gotten, and understandably so, is wouldn't I be better off to put my turbine right here as far down as possible, and then I could have the generator there, and at this point, rather than having the turbine 6 feet below the water surface, I would be 20 feet, and then the remaining foot would just be for the discharge. Wouldn't I be better off like that? And the answer is no, but it's not exactly intuitive. In order to explain it, let's think about this. Why do you think that putting the turbine low is going to matter? The reason you're thinking that is because you have all the pressure above the turbine and no pressure after it. So basically you have 9 psi of water pressure, the entire amount of head, sitting on top of this turbine, and atmospheric pressure, we'll just say 0, after it. And that means the gradient across the turbine is 9 psi. That's what you're after, is gradient across the turbine. Here I've got 6 feet, so maybe I have 3 psi here. So you say, oh, your gradient is only 3, the other one's 9. Well, it's not 3. And the reason is this is a siphon. This entire system is sealed. There's no way for air to get into it, and this is pulling the water through. So what that means is right here, the pressure is atmospheric. It is 0. As you get higher and higher in this tube, you've got a column of water that is siphoning downward, and the pressure behind the turbine, just downstream of it, is actually negative. And in my case, it's going to be about -6 psi. Now, there really is no such thing as negative pressure. Negative pressure for us is negative relative to atmospheric pressure. It's lower than atmospheric pressure behind the turbine, but the differential on either side of the turbine is still going to be 9 psi. So I have not lost any head doing this because this is able to act as a siphon. So hopefully I explained that well enough. How does the draft tube work? Well, this is not a draft tube. This is supposed to be a garden hose full of water under pressure shooting out of the nozzle. And the nozzle is a narrow area and the garden hose is bigger. So, let's say this is on my garden hose out in the yard, it's running at 30 psi. So what is happening here is this water is moving relatively slowly. It is moving down the tube, but because of this narrow section, it's a restriction. The water then has to accelerate to go through that narrow section, and it enters atmosphere at atmospheric pressure. So this is at 30 psi, this is at 0. And what you've done is you've traded pressure for velocity. You've changed pressure energy into kinetic energy. If there is no restriction, the water continues going the same speed that it was going in the hose, and it doesn't shoot out very far. We all kind of know that because we've all played with these things. There's a picture of the draft tube that I'm going to be building. So the ID here is 6 inches, and here it's 12 inches. Now, just like a 6-inch pizza is much smaller than a 12-inch pizza, that's 4 times the surface area at the 12-inch than it is at the 6-inch. The draft tube is really doing the exact same thing, but in reverse. So here we've got high kinetic energy, and here we've got low kinetic energy and high pressure. Coming out of our turbine, we've got high velocity. Just for simplicity, let's say we've got 4 feet per second. And now it's going to come into this draft tube. Well, the draft tube is getting larger. As it comes in here, some of the water is going to go straight. A lot of it's going to start going to the side to fill in those spaces because there's no air or anything else to take that space. So each water molecule has to end up occupying part of this. Now, that's part of why this has to be designed properly. If the angle is too steep, you're going to exceed the vapor pressure of water, and the water is going to boil, and you're going to get flow separation and all these things that I don't know a whole lot about. So the maximum angle you want for this to work right is about 8 degrees. I chose 7 degrees just in case I have any imperfections, and that's 3.5 degrees per side, and you'll see how I end up achieving this later when we build it. But if you think about the velocity of water in this pipe, there's a certain volume per unit time that is coming down the pipe. Well, at the exit of this pipe, it has 4 times the surface area. So that means the same water has to be moving 4 times slower because there's nothing else in this pipe to take up that space. So it's all going to be occupied by the water that was in this pipe. So when it comes out here, it's going to be going 1 foot per second. And what happened to that velocity, it's taking that kinetic energy that was created by the head of the system, and it's converting it back into suction energy. And that suction is going to be downstream of this turbine, and it's going to increase the suction gradient of the turbine. You're not going to get more than 9 psi because that's what the head has available. That's in a perfect system. But the reality is you're taking the kinetic energy and you're adding it back to the pressure differential across the turbine, and you're making the system more efficient. You're getting closer to the 9 psi that is theoretically possible if you had no losses. I try not to repeat myself, but hopefully this kind of makes sense. Here the water is going this way. You're going from high pressure, low kinetic energy to low pressure, high kinetic energy. Here you're doing the exact opposite. Instead of going a narrow nozzle, you're going into a big nozzle. And you're coming in this direction, so you have high kinetic energy and whatever pressure it happens to be at. And after going through the expanding nozzle, you have low kinetic energy and more pressure is generated. In this case, it's suction pressure. So that's how a draft tube works, and that's why they're so useful, because this setup, if you have the turbine right at the bottom and you just discharge it right into your tailwater, you don't have any way to reclaim the kinetic energy of that water. The only way that I know of to do that is with a draft tube and a cone like this. So this system would be less efficient than what we're doing. So what are my options on making something like this? This is just a piece of PVC that I'm using as an example. My first thought was to take a piece of PVC and thermoform it. This plastic, if you get it hot, is easily malleable. This is only a piece of 3-inch, but I could take my piece of 6-inch and using some kind of form underneath it, I could theoretically heat it up hot enough that it's pliable and then form it to the mandrel underneath. That would require me to turn down something like out of a giant log into the inside of what my draft tube needs to be, and then form this around it. Well, it turns out this draft tube is going to be over 50 inches long, 1.3 meters. It's going to be quite a structure, and to be able to take 6-inch PVC and thermoform it that entire length seemed like a tall order. Now you can see I can move it. Parts of that are pliable, and if I could stretch them out and let it cool like that, yeah, there we go, it would stay like that to some extent. There you can see that I was able to form it a little bit. Had to heat so aggressively that I burned it on the outside a little bit. But trying to get an entire pipe hot enough to do that, you know, when it is flexible, it's really quite hot. It's too hot to touch. I would need to make an entire hot box and heat the entire pipe up hot enough, not have it collapse on itself and ruin it, but at the same time being able to form it over that mandrel. That seemed like a pretty tall order. A friend of mine had an idea of using PVC sheet, which is a good idea, because if you just have a piece of sheet, you could then cut out the shape that you need and roll it into a cone, and there's plenty of glues that you can use. Obviously you'd have an end-to-end seam somewhere here, but there's glues that would seam that just fine. You could even have an overlapping piece on the seam, and that would be plenty strong, but you have the same issue. I would have to turn down this giant form and form it around that and get the whole thing hot enough to form it. Seems like a tall order. But then it occurred to me, I happen to have an awesome printer from Bamboo Lab, and it's got a really big print capacity. It can print things that are 12 inches across. Maybe I can just 3D print the whole thing. Yep, Bamboo Lab is the sponsor of this video. So what would I make it out of? Well, there's a filament called ASA, which I won't try to pronounce, and this is like a upgraded UV resistant alternative to ABS. It's very tough, it's good for outdoor applications, prototypes, seems like the perfect filament for me. ASA also bonds well with plastic epoxy, and I can glue it to PVC with the same epoxy. So here we are in Fusion 360, and I'll show you the steps that I took to get here. I had to think for a minute because the draft tube being a cone, you can't use a cylinder. You know, how are you going to make this exact shape exactly like you need? And of course I wanted a socket that I could glue a PVC pipe into on this end. And I'll go back to the timeline, I'll take you through the steps. The bulk of it is all done in the first sketch. So let's edit this sketch, and the constraints make it a little hard to see, but let's zoom in here. All I had to do was sketch basically the cross section of the pipe, and then we are going to revolve this, you'll see, around the y-axis to make a hollow tube. So initially I had to determine what are the dimensions that I want on the socket so that the PVC pipe will fit in and I'll be able to epoxy it in place. And I wanted the exact same internal dimension that the existing PVC pipe has. So that is the radius of my existing pipe. That's also going to be the internal dimension that it starts. So this will be a nice smooth transition there from the 6-inch PVC pipe to our draft tube. The water's not going to see a lip or anything there. And then wall thickness, I chose 0.29 because that's basically the same thickness that I had on the PVC. I wanted the socket to be 3 inches deep. I figured that would be plenty of overlap. Put a little radius there on both sides just to avoid the sharp corners. And then I also put some curves here. You know, obviously I want to avoid pressure points and want to transition from this wall down to this wall. I drew this line at 3.5 degrees off of vertical, enough that this would come out to a 6-inch radius right there. And it turns out that that was 48.64 inches of length of taper that's required. And so I drew that line, and then I drew a parallel line to it, 0.29 away. So yeah, a little careful measuring and some time sketching, and I basically have the cross section of the pipe that I need. So now we need to make it into a tube, and you do that with a very simple command. Let's finish the sketch here, and it's called a revolve. And let me edit this so we can see what we're doing. So I selected the profile, and that is the shape that I drew. I selected the axis, and that was the y-axis here. I selected the extent. Full means you're going to do a full revolution. So I did a 360 degree revolution, and it made it into a tube. 12-inch diameter at the bottom, 6-inch diameter at the top, with the socket for gluing the 6-inch pipe. Now, just so you can see exactly what I'm talking about, you don't have to do a 360-degree revolution. You could do 180, and that would make just half of it. So there, I've only revolved from here around to here. So you can kind of see what that function does. Let's put that back to full. And okay, so that is the vast majority of the work of the draft tube done. I'll go through the other stuff that I did really quick, but basically I sketched another profile there. I extruded it out and did some refining on it. I put a hole through it, and I just wanted a way that I could attach it. I'm not sure exactly how this thing is going to mount, so I wanted some tabs coming off of the side that I'd be able to work with. And actually I moved it up here because my printer can print about 12.5 inches about, and it turns out that the OD of the tube right here is about the max the printer can handle, and with those tabs sticking out past it, it would not be able to print that. So I brought the tabs up high enough that it would be able to print that. And I did some refining on it, and then I did a circular pattern to make 4 of them. And then I also did some additional things to bring it up here. So now I have tabs on both ends. And then the final thing I wanted to do is do a round over where it contacts the tube. And we did that. And now we have a nice curved fillet going into our connection tabs. That's all the rest of that was. And I'm sure I didn't do it the most efficient way. I'm no expert 3D modeler, but for one-off prototypes, this way of doing it works very well for me. So there's our draft tube ready to print, except that's a little bit too tall for the printer. Okay, so here we are in Bamboo Studio. This is the software you use to prepare your models for printing and actually control the printer. So let's take our file, we will drag it in, and there's the draft tube. And I think you can probably see the problem. It is extremely tall. It is showing you how high the printer can print. So yeah, the error, it's over the boundary. So what do? Well, it's actually pretty easy. This is the first time I had ever printed something that's too big for the printer. And you can make another build plate. You can make as many as you want. And what we're going to do is we are going to cut this. And here's the cut icon right here. Click that, and you need to pick a cut height. I found 270 worked well for me. And now, in order to reassemble this after we've printed it, we want some connectors put in between the two parts. So I am going to do dowels, circular shape, and I'll leave their dimensions the same. So I need to place where the connectors are going to be on this orange surface there. So let's look at it straight from the top and get it positioned reasonably well. And I'll just put 3 of them. You actually don't want these perfectly spaced. You kind of want them so that they can only go back together in one orientation. So from looking at it, and maybe we'll move this one over a little bit. This one is obviously longer than the other 2, so that's only going to go together one way. And try to get them all right in the center. Looks pretty good. Confirm connectors. And now we can perform the cut. And now it's going to 3D print those 3 holes for dowels to fit into in that part. And in this part that's remaining, it also has the 3 holes. And somewhere on the screen here, there they are. It prints the 3 dowels that are going to allow you to align those when you put them back together. So I can print that. I still can't print this because it's too tall. So let's go to this build plate. We'll select this. We'll place it on the build plate, and you can do it again. I'll show you again real quick. It's pretty easy. So we've got our model selected. We hit cut. We select our cut height. We'll do the same thing. 270. Add connectors. Look from the top. We'll put 3 of them down. We confirm and we perform the cut. And now there's 3 more dowels. There's another part with the holes on top, and you have the remaining section that's going to need to be cut a couple more times. And here's that project with all the build plates once I have everything laid out. It took 5 main parts to print. Those are all printing in black ASA filament. And just to show you the whole process from this point, say I wanted to print this part, I just hit slice plate, and it's going to take a minute and generate the G code to do that print. And there it has generated the print, and it is going to weigh just over 1 kilogram. It's going to take 18 hours and 28 minutes to do. And this one requires some supports underneath my tabs. So then you want to print it, you just hit print, and it will send it off to the printer and make it happen. Now we need to get this printer running, because this might take a while. So I started out with a test. This is ASA, but it's red. I don't have any plans for this filament. I decided to use that. I wanted to make sure that the socket was going to fit, and I also just wanted to see how it would print. You can see there's some little bumps on the surface. That's very common with ASA. It's a high temperature filament. It's not very easy to print, and you tend to get some over extrusion. I probably could have fixed this by messing with the settings and slowing the print speed down, but on these purely functional parts that are taking over a day to print, I didn't think that was necessary. They're going to work just fine. So yeah, I actually found that this socket was just a little bit too small, so I went back to Fusion, I adjusted the size of the socket slightly, and then re-rendered the draft tube, and that was the final version. So good thing I printed out this test piece. You can also see that those bumps are much less pronounced in reality. That very close-up camera in the printer makes things look a lot rougher than they are. It's hardly even noticeable. For a functional part like that, it doesn't matter. Piece of sandpaper, it comes right off. So no big deal. And now printing the real thing in ASA black. So in order to do all this printing, I'm printing in ASA, which lets off a lot of fumes. You don't really want it in your house. You don't want to be breathing that stuff. I decided to move my printer outside. It's underneath a porch and won't get wet, but it allows me to print this and not have to deal with all the fumes. And it's been doing great. You can see it cranking out one of the draft tube sections there. Now, Bamboo Labs sent me this AMS HT. This is another automatic filament feeder, so this can feed filament to the other nozzle. It keeps it enclosed in a air-proof container so that it doesn't pick up moisture, but it's also a dryer. So, and this one can do high temperature drying. So this is really nice because this can dry the ASA filament before I load it into the main AMS to go to the printer. So this can dry it faster than this can print it. And that means I have a constant supply here of good dry filament that I can use to make my draft tube. It's like my own little manufacturing hub. Yeah, I'm definitely liking this H2D printer. Thanks to Bamboo Lab for sponsoring this video. If you're in the market for an awesome printer, you should definitely check them out. I will leave links in the description. Well, that only took like 10 days of printing. That did take a while. I had a couple of false starts. My 0.4mm nozzle got clogged a couple times and messed up a couple prints. That's also a very common thing with ASA. I went to a 0.6mm nozzle and didn't have any problems after that. That's no joke, man. You never know what I'll get into next, but this is probably the biggest thing I'll ever 3D print, I would imagine. I mean... And very cool that it's exactly a 7-degree angle. That should work very well for our purposes. I'm just going to need to glue it together, smooth out the inside as I go. So before I can put the draft tube in place, I need to get the pipe that is going to be glued to in place. And I need to figure out exactly where that's going to be and get it at the right angle. So that means setting up my new generator Y. There are several reasons that I wanted to redesign this part of the system. This is the original. I'm going with this Y for the next one, and you can see this Y is bigger than that. It might be a little hard to show you, but the inner diameter of the actual Y is wider than the inner diameter of the pipe. So this is a stub of pipe that's glued in, and right there is a step. And then again, on the other side, we have another step. And stuff like that just introduces turbulence. So I decided to go with a Y that actually matches the internal diameter of the pipe. So that's one reason. Another reason is the bearing that I put in here with 3 holes drilled through it. The new turbine that I'm going to be using uses a stator. So I don't need this. The stator can have a central bearing to support it. So that would just be an energy drag and doesn't need to be there. So I want to eliminate that. So there's another thing a bunch of people suggested that I do, and that was to get a piece of clear pipe so that the turbine could actually be in a place where we could possibly see it if the water's not too murky. That's a cool idea, but if you price that pipe, it is like $60 a foot. And it's just horribly expensive. So I bought a piece of clear pipe. Because yeah, that's a cool idea. And yes, this was $120 plus shipping. And it has a touch of a blue tint to it, but I mean, you can see through it. All the stuff that I found that's actually Schedule 40 had a blue tint. You know, we might need to use a flashlight or something. I'm hoping when we get this all done, we will actually be able to see the turbine in action. And another thing that a new generator means is a new diverter, because the old one's glued in and it's actually different dimensions because it's a different Y. And this one's also printed in ASA. That H2D printer just did a beautiful job of it. So this guy goes in here like this. So the water's going to be coming in this way and the turbine's going to be up here. So this is where the clear pipe is going to go. Clear pipe will be in like this, and we'll be able to see the turbine, and the stator will be fixed in here, and then the shaft will be supported by the stator. So that's the plan. For now, let's glue this diverter in. Using JB Weld plastic bonder. This Y is not perfectly round, so there are some areas that there's gapping. So I'm going to put quite a bit of this on and then use it to kind of fill those gaps. So we're going to use a lot of it, probably all of it. Because it wasn't perfectly round, it was gapping right there, and that's where the water is going to be coming in. So I clamped that down, and I'm going to let it dry like that. But there's still some slight gapping that I'm going to need to work on. But I'm going to go ahead and let it dry so that it's in position, and then we'll work on filling those gaps in. At this point, though, I mean, it's fine. It would work, but I'll make it better. And here we are after sanding. I went up to 180 grit. That feels perfect. Can hardly even feel the transition. And this is a drainage hole to allow any water to get out that gets behind the diverter. Now what I'm going to do, rather than gluing this in place, is I think I'm going to put grease on it and just slide it in place. And then I may reinforce the joint because I'm going to have something up above that I could run like a ratchet strap down between the two and hold it together. That way if I ever need to disassemble or change anything, I'll be able to. So I'm going to use this Super Lube synthetic grease. Alright, there you go. It fits in there very tight. I really don't think I'm dealing with enough pressure to do anything to that. I mean, I had to put all my body weight on it to get it in there. PVC fittings are actually tapered a little bit, so the further in it gets, the tighter it gets. Yeah. Now, while I'm working on this thing, I think I want to cover that up with something just to protect it. I don't want to get all scratched up. I just put a piece of bed sheet on it and forgot to hit record, but you know, whatever. I thought about using cardboard. I didn't want to do that because it'll get wet and start disintegrating. This can get wet and then dry out and stay there for a while I'm working on this thing. And actually, once I have this thing done, I'm going to need something to cover this long term because this stuff is not UV resistant. And I don't want to paint over it. Yeah, maybe make a canvas cover or something like that. I don't know. We'll figure something out. All right, a little fiddly, but I got it placed where I want it. And using the laser pointer, I can see it's gonna go into the pool about right there. That's gonna be draft tube, so rather than being a 6-inch pipe right there, it's gonna be bigger. But all the water's going that way and the pool's deep. That should do it. So now I have the enviable task of getting that down pipe attached perfectly where it needs to be so that it will not slide down, it will not move in position at all. And every time I take the generator head off, it will line up perfectly and not fight me. The other one was not quite in line and it was difficult to get those fern coes on and off. So I'm gonna get this as close as I can. This is definitely a little harder than I was expecting. Put a lot of work into this draft tube. Anyway, I've got this pipe kind of held in position where I want it. It's not an easy thing to do when you've got all this unstable ground. How do you support a pipe in exactly the right position? But I got it there. I put a little support between the tree and that T-post. I put this on there, cantilevered out, and then one of those brackets so it's got hold of it. On top of that, I squeezed a hose clamp around it right on top of that bracket so the pipe can't slide down. And it is exactly in line now. On the lower end, right now, what I have supporting it is that board across the ditch and then a ratchet strap just holding that end up. And I need to permanently support it in some way that'll last. And I realize the only thing I really have here that is a solid fixture to attach to is the bedrock. This hillside can move and erode and all that kind of stuff. So that's the plan right now. You may not realize this thing's going to be very heavy when it's full of water, so it's got to be pretty well supported. If it was horizontal, you need to support it every 5 feet. With it being, you know, beyond 45 degrees, I can probably get away with every 7 or 8 feet, something like that. I think I'm good there with that underneath it. I think that's fine. I probably will put something across there just to keep that from going down. But at the bottom, not only do I need to support it vertically, I also need to support it side to side because, like right now, it can swing and we don't want it doing that. So it's going to take some doing. My first step's going to be to pump this thing empty so that I can work down there in my favorite place. All right, most of the way pumped out. So I've got that entire face of rock to work with. I was thinking about what I wanted to use, and I have an old tree stand that fell down, and it's almost like the perfect thing. If I bolt the two ends to the rock and then attach this, I'll probably be cutting this off, but attach this up here to the pipe, it won't be able to rock side to side, and because the pipe is going to be fixed at the top, all it can do is push straight down on those points. I think that'll work. So I've got it positioned where I want it, and I can drill a hole there for an expansion bolt, and then another one there. And that will fix that in place. And then all I have to do is come up with a way to attach it to the pipe. Well, the rock strikes again. This is just one of those vibratory hammer drills. It doesn't have a chance of getting into that rock. So I gotta figure out how to get my old SDS rotary hammer working. All right, so the problem with my hammer drill is it's cordless. I wish it was corded. And it's 24 volt. The batteries are very expensive, and you can't make an adapter to any other battery because none of the rest of them are 24 volt. They're all 18 or 20. What I do is quite a rig. I've got some wires that plug into the battery terminals there, and then go to jumper cables and 2 car batteries to make 24 volts. And it's a pain, but I hardly ever use this thing, and it works. So that's what we're gonna do. Here I'm installing the expansion bolt. Yeah, there's the bolt installed. You just pound it in with a hammer and then thread the nut down. I haven't tightened it yet. And now I know where the other one needs to go. So I'm gonna have to put the phone down, but I'm gonna try to drill that like that. There's the hole right there. This one's gonna be in the water. Ooh. Yeah, I need to tighten that a little more, but that's going to prevent it from going side to side. And now I just need to attach it to the pipe. So I had actually used this and then decided I didn't need it. I had welded on this extra piece, basically to be able to use it on this 45-degree pipe. Anyway, look at that. All I have to do is drill holes in the right place, and I can bolt that together. And that is going to be super solid. And then this will cinch down on the pipe, this bolt here. And for good measure, I'll probably put a hose clamp around it so there's no sliding down. Yeah, that'll do, pig. That'll do. I think this is the final product, or pretty much. I ended up putting a third bolt in to make it rigid this way, because when I take the pipe off, that thing would flop down and then it would be a pain to get it back together, at least by myself. And I figured that would just make it stronger anyway. The draft tube is going to start like here, and so all that's going to get replaced. I will probably do some additional supporting of that. I'm kind of looking at this thinking maybe, because I've got those tabs sticking out, I could put a bolt there and a bolt there and run a cable underneath, something that it can kind of sit on to catch any weight. Because that will be pretty heavy. A 12-inch pipe full of water is a lot of weight. Here I'm taking off the ratchet strap that was holding the pipe. We are on the new support. It feels really solid. It won't let it go side to side like the strap did. And I went ahead and slid the hose clamp down so that it's up against this bracket, and that will prevent the pipe from sliding that way. I crank that down really tight. Ah, click. I can hear it squeaking against that wood up there when I jerk it around, but yeah, I think we're good. Other than what I do once I get the draft tube on here, that's done. Oh man, thank goodness. I will tell you, that doesn't look like much. That took entirely too long. I don't know why that was so difficult. It's kind of a tough area to work in. You're going back and forth to the shop all the time. I don't know. That took entirely too long. Thank goodness it's done. All right, let's get the draft tube on there and be done with this job. I just marked the water line on the pipe because I need to know exactly where that is so that I can make sure the draft tube ends up in the right place. You obviously don't want it up out of the water. You also don't want it down too low. So now to put the draft tube on, I've got to take this pipe off. So there's my water line, and I did some modeling and I need to cut off 37.8 worth of this pipe. Alright, you might be asking yourself why I'm doing it like this. I can't glue this whole thing up as one because then when I go to glue this onto here, which I'm using epoxy, it's going to goop out and not line up well in that joint there. And this thing's over 4 feet long. I'm not going to be able to reach up in there and do anything about it. So I'm going to glue this thing in stages. I'm going to glue right here, and then I'll sand all this, get it nice and smooth, glue the next piece, sand it, glue the next piece, sand it, and work my way down so that it's nice and smooth inside. We're gluing it with a plastic epoxy. So you actually don't want a super tight, you want some room for the epoxy to live in here. So this thing is not, it's not real snug on there. It can wobble around a little bit. I'm going to sand in here, sand that, and then we're going to epoxy that together, and then I'm going to reach in after it dries and we'll clean up the inside. This might take a while. I also had an idea of using a card scraper to help smooth out the inside of this print. A card scraper is typically for woodworking, for surfacing wood with little or no sanding required. Yeah, that very quickly knocks off all those high spots. A lot of times when I mix up epoxy, I mix up way too much. This stuff does not seem to be that way. Need a lot of it. An entire tube for this joint. Luckily it's pretty cold in my shop, which gives you additional working time. It says 6 minutes on it, but it seems to give you longer than that. And I use some ratchet straps to help hold it in position while that's curing. First one down. That probably is going to be the hardest one. Certainly needs the most glue. It's been a little over an hour and that stuff is set up. So now I hope to use the card scraper and we'll smooth out that joint there. Yeah, see, that just scrapes the high spots right down. So I'm going to scrape and sand. There's not much to see because I can't really see while I'm doing it. And I'll show you the end result. You can still see, like, so these scratches here are going to get sanded when I do the next piece. Back in here, it all feels perfectly smooth. And I sanded it to, I think it's 180. Certainly good enough for who it's for. Yeah. Nice joint, no gap. That is good enough. So now we can put the next piece on. How many times in my life will I do that? Blow everything off my workbench with the air. Damn it. You. Yep, right in the trash can where just dirt and junk got all in that glue. Had to clean it off and put on fresh stuff. So that glue is supposed to be stronger than the base plastic, so kind of like gluing wood together, that should be good to go once it sets up. For the next ones, I'm going to use my body to hold it in position while I'm getting the ratchet straps situated. And you guys were kind of in the way of that. Jerks. While that's curing, I have a little more work I want to do on this support. Obviously, I was kind of just throwing this thing together, trying to figure it out. It turns out that this vertical tube here is doing nothing. Yeah, that vertical there is now a heck of a lot stiffer with that. All right, this is after sanding number 3. It feels better than it looks. Perfectly smooth. And now I can glue on the 4th section. This one didn't want to seat all the way in the dowels, so I was hitting it with a rubber hammer. And this ASA is pretty tough. I'm hitting it pretty hard, not hurting a thing, and it does seat down in there well. While that's setting up, it's back to the support bracket. Geese are having a party down there. They didn't invite me. Typical Canadians. Uno más. One more round of sanding, and this thing is finally almost done. Not done. Almost done. All right, there it is. All almost done. Finally. Sort of. Well, I didn't really think about this part. I could go get some help to be safe, or I can try to do it myself and hope I don't drop this thing and bash that draft tube into pieces. That would really stink. Well, let's see what happens. It's probably not apparent. This pipe is pretty heavy. I think it weighs about 75 pounds, and being so long, it's a bit cumbersome to manage. And I don't want to bash against that draft tube. I did put a strap underneath this board to kind of catch it, and with those tabs sticking out that I printed on the draft tube, I knew I would be able to hook it on those and prevent it from sliding all the way down. I got it in the bracket easy enough, but it slid down further than I wanted it to. It was interfering with the Y up at the top, and I couldn't get it to go back up with that Y still in place. So I bolted it in position where it was so it wouldn't slide down. Went up and removed the Y, got it in the position it needed to be in, and then bolted it down permanently. What do you think? I mean, I think the fact that it's going to be going pretty slow coming out of there. I wish there was a little more clearance around it, but I don't really think it matters. The water is just not going to be moving that fast. What I'm talking about is the clearance between the exit of the draft tube and the rock. If it's too close, it's going to cause turbulence, which causes back pressure and restricts flow. And there's a bunch of debris in the bottom of that I'm going to scoop out with the excavator when I clear this. And I think before that thing gets all wet, I'm going to go ahead and get some paint on it. Might as well. I'm going to clean it off with some alcohol. I did give the outside a quick sanding, by the way. All right, we're using Krylon Fusion. This is for plastic. It says any surface, but it works really well for plastic. Now, obviously, I chose ASA because it's UV resistant, but it's not UV perfect, so this paint is just going to help extend its life. I want this thing to outlive me. Some serious fumes down in there. I'm going to two-coat the top once that dries. All right, moment of truth. Is this thing going to line up? Oh, look at that. That's what I'm talking about. I was fighting all the time before to try to get this to slide up over and misalign joint. That's perfect. Yep, I can deal with that. All right, there it is. Draft tube is done and installed. Now, I would love to open it up and at least see it working, but there's two problems. One, I need to support the draft tube before I let it get full of water, and I have a plan for that, but I'm waiting on something. And the other thing is I would need to have the water, give the water a place to go. Right now, we have this rock bridge that I built to get across my channel. That all needs to be removed before I can open that up and let it start really throwing some water out of there. So that's a lot of work to do. This video has gotten long enough, so we're gonna have to do that in the next one. Now, I will say I bought another gadget that is gonna allow me actually to quantify how much the draft tube helps. I think. We'll see. I've gotten way more invested in this hydro system than I ever thought I would get, but I'm having fun. You guys seem to be interested in it, so we're going to keep on plugging along and see what we can get out of this thing. But I am really happy to have that done. That was a big hurdle, a lot of unknowns, a lot of things that I've never done before and just wasn't sure how it was going to go. And I'm pretty happy with the result. A little more work to do on it, but yeah, all the hard stuff is done. That thing's pretty much ready to go. So we are getting very close to actually doing some testing with a complete system. There's been some developments in the turbine department, in the testing department, all sorts of things going on. This is going to be really cool. So the next few videos are going to be interesting. Thanks for watching. We'll see you then. Little bonus footage. I did take some of my failed prints and I glued them together with some of the leftover glue. Now this glue was already setting up a little bit when I did it. I think the ones that I actually glued up that are in the draft tube would be as strong or stronger than this, for sure. Like, this likely, because the glue was getting stiff, is probably not as strong, I would think. Wow. Well, that's a good sign. That's a real good sign. Alright, I mean, you can break it, but you're gonna have to do some damage on it. I ripped the tab off right there. I'm pleased with that. I think the draft tube is gonna hold up very well based on how much force that took.